For our lesson, next lesson, chapter 6, 6.2, the natural base E is what we are talking about today. And looking at that, natural base E is an irrational, sometimes just called the natural base. It is defined as this function there. What it is used for is looking at how we can calculate things that are compounding continuously. So E is a constant, just like pi is a constant, right? We're used to this mathematical concept of pi, right, being equal to a number, right? 3.14159, and it goes on forever and ever, right? It is an irrational. Natural base, or E, is the same thing in that it goes on forever and ever. So it is approximated at 2.71828, and then it goes on from there. So, like I said, it's used for calculating constantly compounding interest or growth. John Napier first looked at it, or was given credit for first looking at it, and then Jacob Bernoulli, a famous mathematician and scientist, introduced that constant value in 1683. He was looking at continually compounding interest. Leonard Euler gets the most credit for this natural base. It's even sometimes called Euler's number. He was working on a publication in the late 1720s, looking at the explosive forces of cannons, and was using that constant of the natural base. Today we use it for still population growth, constantly compounding interest, and the radioactive decay processes. So it has plenty of actual use in today's society. Natural base, if it has an exponent, you can use all of the normal exponent properties that we use any other time. So you can say, okay, I have e to the third times e to the sixth, right? So just like any other exponential, we are going to add those exponents. So it would be e to the ninth power. If you ever get hung up on exponent properties, I can't remember, do I multiply them or do I add them? Natural base E is a good way to review those on your calculator. Looking at the calculator screen, right with the division sign, the second division sign gives me that lowercase e for that natural base. So I could say natural base to the third power times natural base to the sixth power, right? And it will calculate that out for me. And then I can check my work with natural base to the ninth power, right? So that would refresh my memory. Oh, yes, I do add those exponents. If my work in my calculator was not correct, I had done something wrong. Looking then at the next one, dividing, right? Natural base to the fifth power divided by natural base to the fourth power. We're going to subtract those exponents. So that would be e to the first, or just e. And then 16 divided by 4 is 4. Looking at example 1c, right, we're going to square everything inside the parentheses. So we will essentially have 3 squared times e to the negative 4x, also squared. You will probably, in reality, mental math this step. So this would be 9 e to the negative 8x. And then for a fully simplified answer, then this negative 8x would need to go below the fraction bar. E to the 8x. That's going to go down below the bar. Right? Negative fraction, negative exponent means it's on the wrong side of the fraction bar. And then for example D, this is a square root, right? So this is a little 2 right here. you are going to square root everything under the radical. So square root of 4 is 2. And then for square rooting e to the 2x, you're going to divide the exponent by 2. So that just becomes e to the x power. So that is using exponent properties with our natural base. Natural base can be graphed. We have these natural base functions on the screen now. That is kind of the parent function of the natural base with a positive x value. It's exponential growth. And then when you have, when you see here in the second graph, we have this e to the negative x right here. That's what gives us exponential decay, right? So they follow all of our other exponential graphs. Exponential function properties, we would still have our domain being all real numbers, our range being y is greater than 0. That still holds true. So for graphing these, determining whether they're exponential growth or decay, right, the best thing to do would just be to plug it into the graphing calculator. So we would say 3e to the x power. I want to throw some parentheses around that exponent just to be sure that we're doing things correctly. And when I graph it, right, I see this nice exponential growth function on the screen. To build that, I would need to go to table and get the data that I need. The problem becomes we don't get a lot of clean whole number data when we're dealing with natural base. So this would be 0.40 or 0.41, and then this would be 1.10, and then 3, and then 8.15, right? So I'm getting all of that from table on my calculator, and then I have to do some estimating here as I am plotting my points. So as I plot those out, I didn't do a very good job of drawing my line there, but that's nothing new for me. So this one here would be exponential growth, right? We see it increasing as x increases. For example B, we are going to again go to the calculator, and we are going to graph e to the negative 0.5x. I can hit the graph first to see what I'm kind of dealing with. I see an exponential decay function, so you could even go ahead and write that in now based on what you see on your calculator screen. Right, there's my decay function, and then I would go to table just like I did before, graph it up. Right, so I get negative 7.4, not negative 7.4. I don't know why I said negative. And then 2.7 here, 1, and 0.4. So we come in, we graph our points. So a little better there. It's still not a very smooth line, but you get the idea. So we get that exponential decay. And again, that exponential decay comes from that negative in the exponent. Previous lessons we've looked at compounding interest on a set time schedule, represented by this equation here. Not the tool I wanted, but the A equals P times the quantity 1 plus R over N to the N times T power, right? So that's if you have a traditional bank account where they say, hey, we're going to give you 4% interest compounded monthly. you use that equation. The continuously compounded interest formula, which I've never seen a continually compounded interest account, but it is the A equals your amount in your account is equal to principal times that natural base, and then your exponent is your annual rate times time. So looking at that, if I had a situation like this one here, you and a friend each have accounts that earn annual interest, compounded continuously. The model in your account after T years is modeled by A equals 4,500 times natural base to the 0.04 T power. And then your friend's balance is shown by the graph. So they have a couple questions there for us. They want to know who has the greater principal, right? So I would probably just divide my workspace here into a couple of sections, right? Here's me based on the formula, and then here's friend based on the graph, right? And the first question is who has the greater principal. So for my friend, we see here this 0,4,000 point. So friend's principal is 4,000. And then my principal comes from this equation here. So my principal is 4,500. So I have the greater principal after, or a greater principal initial investment. And then they want to know after 10 years. So in year 10, for friend, I go to the graph. That would be about right here, right? So I would bring that over to, I could say that's about $7,200 would be about what my friend might have, 7,300, but somewhere in there. For my account, I am going to have to take my formula, 4,500 times natural base to the 0.04 times 10 power. And that is 100% going to be a calculator problem. So I could just type that in just like it's shown, 4,000 natural base E, and then make sure for my exponent everything is in parentheses, the 0.04 times 10, all in parentheses. Right? And then I hit enter, and after 10 years I have $6,713.21. Right? So friend started with less money than me, ends with more money than me. So friend obviously had a better interest rate than the 4% that I was getting in my account. So good for friend. That brings us to the end of the lesson. Make sure that you get your assignment completed and reach out if you have any questions.